Hi. I wanted to talk this evening about problem number 10 that we started working in class today and ran out of time for because of the drill. But I wanted to take the opportunity to also share with you the big picture of physics. Or at least of physics modeling. The big picture is that we're going to have physical laws that are going to give us usually not information about what we're interested in, but in its information about its derivatives. And so those physical laws are going to give us some kind of differential equation. Or DDQ for short. And then we're going to take that differential equation and use various methods to come up with a description, to come up with a model for the quantity that we're interested in, for the phenomenon. Because these two are so tightly tied together, very often the differential equation itself will be called the model. Now, what do I mean by a differential equation? Well, simply put, a differential equation is an equation that contains the derivative of some function. More specifically, usually we're going to write the differential equation in the form dv dt equals some function. And that some function could be a function of t and v, or it could be a function of t alone. Likewise, we can have a dx dt equals some other function of t and x, and so on and so forth. So these are differential equations, but they often come also with initial conditions, such as v of 0 equals 0, x of 0 equals x 0, that kind of thing. And so what our aim is in solving the differential equation is to take this dv dt equals t comma v and use various methods to get v as a function of t, or to get, in the second case, x as a function of time t. So what we're trying to do essentially then is to take a rate of change and use that rate of change and reverse engineer the original function whose rate it was. It's like derivative jeopardy. I'm giving you the derivative and you are giving me the original function from which it came. That's the big picture. Now, what does this look like in practical application? Let's consider a phenomenon that we have talked about before. Let's consider constant acceleration. And in the case of constant acceleration, what we really have is the derivative of velocity, which is acceleration, is a constant value a. And so this is a differential equation, one of the easiest kind, in which our derivative of velocity is constant, and our initial condition is that our velocity at time 0 will be v0. And our goal now is to take this information and come up with an equation for time, for velocity, as a function of time t. We call this the solution to the differential equation. So notice that the solution to the differential equation is a function. Okay, well, what about those various methods that we talked about? Well, the easiest of the various methods is to undo a derivative with an integral if you can. And that process, method number 1, is about 50% or more of the differential equations that we encounter in this class are going to be solved with method number 1. Sorry about the typo there. Okay. So how does this actually work? We start with our differential equation, and now we are going to separate the variables by multiplication and or division. Specifically, we're going to multiply both sides by dt. Now this requires a little bit of subtlety here, because you remember that dv dt was not really a quotient, it was really the limit of a quotient. And so is this legitimate? Well, no and yes. No, in the sense that I am not really just multiplying both sides by dt, even though it looks like this. But yes, in the sense that I now end up with a new equation in what we call differential form, in which I have two quantities called differentials that are little changes in each quantity. So dv represents a small change in velocity, and dt represents a small change in time. And what this equation here is saying is that a small change in velocity will always be equal to the acceleration times the simple change in time. So if my time changes by, let's say, 1 millisecond, so that dt is 1 millisecond, and let's say my acceleration is 10 meters per second squared, then the resulting change in velocity will be 10 times 1 millisecond, or 10 milliseconds. Oh, it has the units of meters per second. And notice that the units work out, right? This is a times dt, so I get meters per second squared times seconds gives me meters per second. Okay, so this is the differential form, and what it's doing is making a statement about changes and how those changes are related to each other. And now what we can do is to add up all of those changes by anti-differentiating like so. And when we do, what we get is the entire velocity equals a times t plus a constant c. And the constant c is necessary because when I anti-differentiate, I am finding all possible functions whose derivative is a. Well, what is the value of my arbitrary constant c? The value of c is uniquely determined by the initial condition. Let's go back and look at that initial condition. Here it was, right here. V of 0 is equal to V0. And so if I use the initial condition by substituting 0 for time and V0 for the velocity at time 0, then I discover something really nice, which is that my arbitrary constant c is just equal to V0, or the initial velocity. And substituting that back in for c gives me the equation that I knew was coming because of my previous experience, and that is V equals V0 plus AT. So, to recap what we've covered so far, we started with a differential equation giving me the derivative of the velocity as a constant. And we took and integrated that differential equation. We applied the initial condition to get a unique solution for the velocity as a function of time t. This process can be repeated because the velocity itself is the derivative of position. So, although we have velocity as a function of time t, it is also the case that we now have a new differential equation. I take and simply replace or substitute dx dt for the velocity. Now I get a new differential equation, and I can supply an initial condition, let's say x of 0 is equal to x0. And I can repeat the process of separating the variables by multiplying by dt. And this new equation in differential form is saying something very interesting about how x changes when t changes. Dx is a change in position. Or a very tiny displacement that occurs when time changes by dt. And what's interesting about this, in contrast to the previous, is that my dx now is not going to be a constant times dt, but instead will be equal to v0 plus at times dt. In other words, as time goes on, the amount of position change that I get will itself be changing because of the term at right here. In other words, the velocity is changing. So going back to our previous example, if a was 10, then as time went on, the amount of displacement that I would get for a small change in time would be increasing for increasing values of t. Having separated, we can now integrate or anti-differentiate. And go term at a time. On the left-hand side, we get x. On the right-hand side, we get v0t plus, using our power rule, 1/2 at squared, plus another constant c. And I'm calling this one c1 just because it's different from the previous constant c. Well, what is the value of c1? To get the value of c1, we use the initial condition. And when we do, we find out that x of 0 is going to be equal to v times 0 plus 1/2 of a times 0 squared plus c1. That's just a lightly easy expression to evaluate. That gives me c1. And x of 0 is x0. So we conclude that c1 is equal to x0. Or in other words, x equals v0t plus 1/2 at squared plus the initial position x0. So, all of this is a long-winded way to say that when acceleration is constant, we necessarily arrive at the equations of motion that we know and love. Now, how does all of this relate to number 10? Let's take a look at the question. In number 10, we are told that we have a snowmobile originally at the point with position vector 29 meters at an angle that is 95 degrees counterclockwise from the x-axis. And it is moving with a velocity of 4.5 meters per second at an angle of 40 degrees. And it is experiencing an acceleration that is constant of 1.9 meters per second squared at an angle of 200 degrees. And when we give all these their appropriate units, there we go. And they want to know now, after 5 seconds have elapsed, find position of the snowmobile. Okay, now let's do some preliminary understanding of what's happening, because these pieces of information are not all exactly the same. The acceleration is an acceleration that is constant, that is going to not change over time. And so for that reason, this acceleration we want to think of as applying during the entire 5 seconds. But because there is an acceleration, necessarily the velocity will change. And so I need to indicate that fact by observing that this is an initial velocity given to us. That this velocity is true at the start of the problem, but because of the acceleration, it's going to change. Likewise, this position is the position at the start of the problem, but because of the velocity, it is going to change as well. And in particular, what we have is a snowmobile that is here at 2.90. It is experiencing currently a velocity of 4.5 at an angle of 40. But it is going to experience an acceleration that is going to push it in this direction right here. And as a result, the velocity vector is going to change. And as the velocity changes, so also the position is going to change according to the velocity. So that's the picture. Now, the information they give to us is in a horrible form. We need it to be in rectangular form, and so we do that. So when we do all of these conversions from rectangular to polar, which are a little bit of a pain but are necessary, then what we find is that the initial position is equal to negative 2.53i plus 28.89 j. And the initial velocity is 3.45i plus 2.89 j. And the acceleration is going to be a constant negative 1.78i minus 0.65 j. And now what we'd like to do is to find the velocity and the position after 5 seconds have elapsed. Now here's where we get to leverage our work with the differential equations. Because my acceleration is constant, I have already solved the differential equations when the acceleration is constant. In particular, I found that when acceleration is constant, that the final position is equal to the initial position plus v0t plus 1f at squared. And I have found that when the acceleration is constant, that the velocity is equal to v0 plus at. And so now I can leverage all of that work very simply by doing v equals v0 plus at. But, you ask, does it matter that my acceleration and initial velocity are given to me as vectors? Not at all. Because what happens in the x stays in the x, and what happens in the y stays in the y. And so as a result, I can treat the x components and the y components as independent of each other. In other words, I can directly plug in 3.45i plus 2.89j for my initial velocity. And I can directly plug in negative 1.78i minus 0.65j times time. And this is now the velocity as a function of time. And in particular, after 5 seconds have elapsed, I can say that v of 5 is 3.45i plus 2.89j plus now negative 1.78 times 5. Substituting 5, well, let me go ahead and write it. So distribute the 5 to each of the terms there, and get 3.45i plus 2.89j. And this is going to be minus 8.90i and minus 3.2j. And now it's a simple matter of going and collecting all of the I terms and all of the j terms. And when we assemble all those in one place, then we find that our new position is going to be negative 4.35i, and is going to be negative 0.36j. Now, the moral of the story then is that we can use the same equations of motion, but we're going to treat the i's and j's separately. Some people like to actually split this up into x's and y's completely separately. And if you do that, then you would take all your x components here, right here, and you would treat these as components for the x. So you label this one as Rx, 0, and this would be Vx, 0, and this would be Ax. And you would take all these components right here, and you label them as Ry0, and Vy0, and Ay, and then you would do entirely separate calculations for the x's and for the y's, and at the end, you would still find that the x component was negative 4.35, and the y component would be negative 0.36 meters per second for the velocity. We do the same kind of thing for the x of t, the x of 5. We use our previous solution to the differential equation. X of 5 is going to be equal to x0 plus v0t plus 1/2 t squared. And we now plug in all of those components. Negative 2.53i plus 28.89j is the initial x0. I used x. I'm sorry, I do that sometimes. These should be r's. There we go. If you were confused. Now the reason that we have these r's here is that rather than x's is that because we're doing motion in 2 dimensions, we're really going to think of x as the horizontal and y as the vertical. So as we work, we have the initial r0 right here. We have the initial v0, which is 3.45i plus 2.89j times time, and then finally plus 1/2 of negative 1.78i minus 600j t squared. And you can plug in t equals 5. So this was r of t, excuse me. And then you get r of 5 and plug in and simplify. And when you do, you get that the final position is equal to negative 7.53i plus 35.2j. Now, what's the moral of this story? The moral of this story is twofold. First of all, that our work with differential equations is going to lead us to solutions that we can remember and use in previous situations where the physical laws are the same. So in particular, here I was able to use these two equations of motion, v equals v0 plus at, and r equals r0 plus v0t plus 1/2 at squared, because both of those were derived from the differential equation acceleration equals a constant. When we have, in the future, additional differential equations where acceleration is not constant for whatever reason, then our differential equations will give us new and different solutions. So that's the first thing. The second thing is to observe that we can